Right now, two spacecraft launched before most people alive today were even born are still out there, still moving, still transmitting, hurtling through the darkness at tens of thousands of miles per hour, further from Earth than anything humanity has ever sent into the void. They were built in an era when pocket calculators were cutting-edge technology, assembled by engineers who never expected them to last more than a decade. And yet, here we are, nearly half a century later, still receiving signals from both of them. But that's about to change. The Voyager probes are running out of time. Not in some distant, theoretical sense, in a very real, very measurable sense. The power is nearly gone. The instruments are shutting down one by one. And NASA has exactly one plan left to try to squeeze a little more life out of them before the silence becomes permanent. It's a plan so risky that if it goes wrong, it could end both missions immediately. They're calling it the Big Bang, and it has to work. This is the story of two of the greatest machines humanity has ever built, the slow and graceful way they're dying, and what we stand to lose when they finally go quiet. The story starts in the summer of 1977, when NASA launched two identical spacecraft within weeks of each other. Voyager 2 launched first in August, despite its name. Voyager 1 followed in September. Both were built for a single defined mission: fly past the giant planets, Jupiter, Saturn, Uranus, Neptune, collect data, send it back, and call it done. The mission was expected to last roughly 4 years, maybe 5 if they were lucky. They were very lucky. The planetary flybys were extraordinary. Voyager 1 gave us our first detailed look at Jupiter's turbulent storm systems and sent back jaw-dropping images of Saturn's rings that rewrote the textbooks. Voyager 2 went even further, becoming the only spacecraft in history to visit all 4 outer planets, a feat that won't be repeated for over a century, since the rare planetary alignment that made it possible won't occur again until the 2015s. The images alone were worth the entire investment, but what happened after the planetary phase was something nobody had planned for. The spacecraft kept going, and kept going. Engineers who had designed them for a 4-year mission watched in quiet amazement as year 5 passed, then year 10, then year 20. The signals, increasingly faint and increasingly delayed, kept arriving. At some point, the mission stopped being about the planets entirely and became about something far more profound: the edge of the solar system itself and what lay beyond it. In 2012, Voyager 1 crossed the Heliopause, the boundary where the sun's influence ends and true interstellar space begins. It became the first human-made object in history to leave the solar system. 6 years later, Voyager 2 crossed the same boundary at a different point, giving scientists 2 simultaneous sampling locations in interstellar space for the first time ever. They remain, to this day, the most distant human-made objects in existence. But distance has a cost, and after nearly 50 years, that cost is finally coming due. Both Voyagers run on nuclear power, radioisotope thermoelectric generators, or RTGs, which convert heat from the radioactive decay of plutonium-238 into electricity. It's an elegant solution for deep space missions where solar panels become useless, but RTGs have an unavoidable limitation. The plutonium decays over time, producing less heat, which means less electricity. The Voyagers launched with approximately 470 watts of power each. Today, nearly 50 years later, each spacecraft has roughly 230 watts to work with. And here's where the math becomes genuinely alarming. The radio transmitter alone, the single component responsible for sending any data back to Earth, consumes approximately 200 watts just to operate. What's left after that, the margin available to actually run science instruments, is somewhere around 5 to 6 watts. To put that in perspective, a standard LED nightlight uses about the same amount of power. That is the entire energy budget keeping humanity's most distant scientific outposts alive, and it shrinks every year. The spacecraft lose approximately 4 watts of power annually as the plutonium continues to decay. 4 watts sounds trivial until you realize the total margin is only 5 or 6. Every year that passes pushes them closer to the threshold where there simply isn't enough power to keep even a single science instrument running. The countdown isn't theoretical anymore. It's measurable. It's happening right now. For years, NASA's response to the shrinking power budget has been methodical and, in its own quiet way, deeply sad. When the power drops below what's needed to run everything, something has to go. So the mission team has been switching off instruments, one at a time, carefully, permanently, to preserve whatever scientific capability remains for as long as possible. Both Voyagers launched with 10 operational instruments each. Recently, the pace of shutdowns has accelerated. Voyager 1 shut down its cosmic ray subsystem in February of this year, an instrument that had spent decades measuring high-energy particles streaming through interstellar space, data that exists nowhere else. A few months later, in April, the low-energy charged particle instrument followed. Another goodbye. Another window onto the universe, closed forever. Today, Voyager 1 has exactly 2 instruments still operating: a magnetometer measuring the magnetic fields of interstellar space, and the plasma wave subsystem studying charged particle behavior. That's it. 2 instruments on a spacecraft that crossed into interstellar space over a decade ago, still managing to send back data scientists describe as irreplaceable. Voyager 2 is slightly better off, with 3 instruments running: its cosmic ray subsystem, a magnetometer, and a plasma wave subsystem. But the trajectory is the same. More instruments will be shut down. More windows will close. The only question is how quickly, and whether NASA can slow the process down before it's too late. That's where the Big Bang comes in. Engineers at NASA's Jet Propulsion Laboratory have spent years looking for creative ways to squeeze more life out of the Voyagers. They've adjusted heating strategies, reprogrammed onboard computers from billions of miles away, a task requiring signals that take nearly a full day to arrive, and made careful trade-offs between power consumption and functionality. The latest answer to that question has been given an almost theatrical nickname: the Big Bang. Both spacecraft have 3 heater devices currently running to keep their thruster fuel lines from freezing. In the extreme cold of interstellar space, temperatures approaching 460 degrees below 0 Fahrenheit, those fuel lines need to stay warm, or they'll freeze solid, clog, and render the thrusters useless. Useless thrusters mean the spacecraft can't orient itself. A spacecraft that can't orient itself can't point its antenna at Earth. And a spacecraft that can't point its antenna at Earth goes silent, permanently. But JPL engineers spotted a crucial distinction. The current heater devices do their job at a certain power cost. There are 3 alternative devices on each spacecraft, different components, same function, that use almost 10 watts less power combined. 10 watts. In a world where the entire science margin is 5 or 6 watts, 10 watts is an enormous number. It's the difference between 1 more year of science operations and the lights going out ahead of schedule. The plan is straightforward. Switch off the current heaters, switch on the alternatives, and pocket the power savings. If it works, mission managers estimate it could delay the shutdown of at least 1 science instrument per spacecraft by a full year. But if it goes wrong, if the alternative heaters don't perform as expected, if anything malfunctions during the transition, the fuel lines could freeze. And that would be the end. Not a gradual end, not another quiet goodbye to another instrument. An abrupt, total, immediate end to both missions. The test is underway now. Engineers plan to run the procedure on Voyager 2 in May and June of 2025, then apply the same approach to Voyager 1 later this summer, assuming Voyager 2's results are good. Any command sent takes nearly a day to arrive. Confirmation takes another day to come back. There's no real-time troubleshooting. There's no quick fix, just instructions sent across 15 billion miles of empty space, and then the long wait to find out if they worked. What makes the Voyager's situation so striking isn't that they're running low on power. That was always going to happen. What's remarkable is just how many different things are simultaneously working to end the mission, and how long the spacecraft have held all of them off. The fuel lines are one threat. The thruster system depends on hydrazine remaining liquid enough to flow, and as temperatures push toward absolute zero, that balance grows more precarious every year. The Big Bang buys time, but the underlying physics don't change. Then there are the cameras, already damaged when the spacecraft flew past Jupiter's volcanic moon Io in the late 1970s. The intense radiation around Jupiter essentially blasted them. They've been degrading ever since, subjected to decades of cosmic ray bombardment in interstellar space. They're no longer used for science, but their deterioration is a reminder that every component on these spacecraft is aging simultaneously, in an environment unlike anything on Earth. The computers present their own quiet crisis. Both spacecraft have backup computing systems. The original designers, to their enormous credit, built in remarkable redundancy. Alan Cummings, a senior scientist at Caltech and co-investigator on the mission, acknowledged this at a public event in 2024. There is so much redundancy on these spacecraft. It is amazing, and they built that into it. But redundancy only buys time. The backups are aging just as the primaries did, built using technology that was cutting edge in 1977, but is now more than half a century old. And then there's distance itself. Voyager 1 is currently about 169.8 astronomical units from Earth, 169.8 times the distance from Earth to the Sun. Voyager 2 sits at roughly 143.1 astronomical units. The signals they send back travel at the speed of light, and even then it takes approximately 23 hours for a message from Voyager 1 to reach us. Any command sent back takes the same time to arrive. Any problem that develops requires nearly 2 days of round-trip communication just to attempt a fix. It's not one thing killing the Voyagers, it's everything, closing in at once, slowly and inevitably, like the dark between stars.
So, how much time is actually left? That depends on who you ask and how optimistic they're feeling. Suzanne Dodd, project manager for Voyager at JPL, expressed confidence in 2022 that both spacecraft would reach their 50th anniversary in 2027, and nothing since has suggested that was wrong. Both are still operating. But Dodd has also laid out a more ambitious target. In an ideal scenario, with good engineering, good luck, and no catastrophic failures, she wants to see each spacecraft reach 200 astronomical units from Earth, which would happen around 2035. That's going to take a lot of good luck and good fortune and good engineering, she said. Then she added something that cuts to the heart of what Voyager has always been about. But nobody would have thought that Voyager would last for 45 years. So what's another 15? Alan Cummings made an observation at Caltech in late 2024 that is technically accurate, but also quietly poetic. In a strict sense, he said, the nuclear power on the Voyagers never fully runs out. Radioactive decay always has a half-life, which means some level of energy generation continues essentially forever. The issue isn't that the power stops, it's that it drops below the threshold needed to do anything useful. Below the threshold to run a science instrument, below the threshold to heat a fuel line, below the threshold to transmit a signal home. The Voyagers won't simply switch off one day. They'll fade, gradually, like a signal growing too faint to hear. It's interesting, because the Voyager is coming to an end in kind of a graceful way, Cummings said, because there's different things trying to kill it off. Graceful, that's the word he chose. And somehow, against all odds, it fits. It's worth pausing on what actually disappears when the Voyagers stop transmitting, because it isn't just two old spacecraft going offline. It's something considerably harder to replace. The Voyagers are the only human-made objects ever to directly sample the interstellar medium, the environment that exists between star systems, outside the protective bubble of our own sun. Everything we know about what that environment actually looks like, as opposed to what our models predicted, comes from these two probes. The structure of the Heliopause turned out different than expected. Charged particle behavior didn't match theoretical predictions. The magnetic field environment beyond the heliosphere revealed complexities researchers are still working to fully understand. None of that could have been collected any other way. You can't study interstellar space from Earth. You can't model it accurately without direct measurements. The Voyagers went there. They're still there, and the data they're returning is still, after all this time, genuinely new. When they go silent, that window closes, and there is no replacement mission currently in development that would reach interstellar space within any of our lifetimes. A spacecraft launched today would take decades to reach where the Voyagers are now. The earliest any successor could realistically arrive at the Heliopause would be the 2070s or 2080s, and that assumes such a mission is funded and launched soon, which is far from certain. So when the Voyagers finally go quiet, there will be silence from interstellar space for at least a generation. The most distant frontier humanity has ever touched will go dark, and we won't have anything sending signals from out there for a very long time.
None of this diminishes what the Voyagers have already accomplished. If they went silent tomorrow, they would still rank among the most successful scientific missions in human history. They gave us our first real understanding of Jupiter as a dynamic, complex system. They showed us that Europa might harbor a subsurface ocean, a discovery now driving NASA's Europa Clipper mission. They revealed that Io is the most volcanically active body in the solar system. They discovered rings around Uranus and Neptune, found new moons around every giant planet they visited, and generated data that has filled thousands of scientific papers across multiple generations of researchers. And then, having done all of that, they kept going.
There's a golden record on each Voyager, a literal gold-plated disc containing sounds and images selected to represent life on Earth. Music, greetings in 55 languages, the sound of rain, of surf, of a mother's first words to her newborn child. Placed there by a committee that included Carl Sagan, intended as a message in a bottle for any civilization that might someday find these spacecraft drifting through interstellar space. The odds of that happening are essentially zero, but the gesture itself says something about the people who built these machines, about their willingness to think not just years or decades ahead, but millennia. The Big Bang maneuver belongs to that same tradition, engineers refusing to give up. A team at JPL spending their working hours figuring out how to shave 10 watts off the power budget of a spacecraft 15 billion miles away, because those 10 watts might mean one more year of data from the only instruments humanity has ever placed in interstellar space. It's unglamorous work. Most people will never hear about it, but it matters. Sometime in the next decade, maybe sooner, maybe later, one of the Voyagers will send its last signal. The moment won't be dramatic the way movie endings are dramatic. There won't be a final image. There will just be a signal, and then the absence of a signal. And scientists monitoring the data will note the timestamp and close the file. The spacecraft will keep moving, drifting outward at roughly 35,000 miles per hour, carrying their golden records into the darkness, long after anyone on Earth is receiving their transmissions. In about 40,000 years, Voyager 1 will pass within 1.7 light-years of a star called Gliese 445. In roughly 296,000 years, Voyager 2 will pass within 4.3 light-years of Sirius, the brightest star in our night sky. Neither will stop. They'll just keep going, silent and patient, carrying the evidence of our existence outward into a galaxy that doesn't know we're here yet. The question of how long the Voyagers have left is really two questions. How long can they keep transmitting, and how long will they exist? The answer to the first is probably somewhere between a few years and a decade, depending on the Big Bang and whatever engineering solutions JPL pulls off next. The answer to the second is effectively forever, or as close to forever as anything built by human hands is ever likely to get. When they finally go quiet, it won't feel like a failure. It will feel like the end of something genuinely extraordinary. The kind of ending that makes you stop and think about what was accomplished, and how, and by whom, and whether we still have the will to build things with that kind of ambition. Because the universe is still out there, still vast, still mostly unexplored, still full of boundaries we haven't crossed yet. The Voyagers showed us that crossing them is possible. They showed us that a machine built by human hands, powered by the slow decay of radioactive material, transmitting on less power than a nightlight, can travel to the edge of the solar system and keep going, and still have something worth saying nearly half a century later. The question isn't just how much time they have left. The question is what we're going to do with the silence when they're gone.